Hi everybody, welcome to lecture 22 of Electrical Engineering 331. In this lecture we will learn more about the Fourier series. And by the way, we're just going to do two examples in this lecture, and both of them will be about both of them will concern the cosine-sine Fourier series. But I think that I hope it will be very interesting to you, because it really is pretty interesting to me. I think it demonstrates several interesting ideas. So anyway, let's just jump right in. We've talked about this, I think, a couple of times already this semester, where we have encountered this integral, a definite integral of cosine squared t dt. And so the question is, how do you do this integral? And it's one of these questions where you have to remember a little trick. What you have to remember is that cosine squared t can be written as 1 plus cosine 2t over 2. And once you do that, then the integral is straightforward. Now this raises the question of, well, how do we know that cosine squared t is 1 plus cosine 2t over 2? How can we arrive at this result? And one of the most common ways that you will see people show for getting this result is the following. Okay, you'll need to recall that the cosine of a sum, a plus b, is equal to cosine a cosine b minus sine a sine b. So if you let b equal a, then this becomes cosine of 2a equals cosine a minus sine a sine a, which is the same thing as cosine squared a minus sine squared a. Now, if you also remember that sine squared of a is the same thing as 1 minus cosine squared of a, then, like right here, then you have cosine of 2a is equal to cosine squared a minus 1 minus cosine squared a, so you get 2 cosine squared a minus 1. And then if you take this 1 over to the other side of the equation and divide by 2, you arrive at the desired result. Cosine squared of a is equal to 1 plus cosine 2a over 2. Or, of course, if we substitute t for a, then cosine squared t is 1 plus cosine 2t over 2. So that is one way to arrive at this result. But in the derivation of that result, we had to remember several things that could slip your mind. So that raises a question of, well, is there any other way to obtain this result? And the answer is yes, because if you look at this and think about it for a moment, you'll see that this is actually just a cosine Fourier series for cosine squared t, which is really pretty remarkable, but it's true. And so, yes, you could obtain this by calculating the Fourier series of cosine squared t. So let's do that and see what happens. And I think you'll see that this is pretty interesting. Okay, so as usual then, we will say that cosine squared t is equal to a naught plus the summation n equals 1 to infinity of a n cosine n omega naught t plus b n sine of n omega naught t. Now, as usual, the first step is to find t naught, the fundamental period. And so the fundamental period, I'm pointing out here, the fundamental period of the cosine of t to the first power, of course, is 2 pi. And so because of that, you might be led to believe that the fundamental period of cosine squared t is also 2 pi. But if you graph this, you'll see that actually the fundamental period of cosine squared t is pi. So here's the way it looks. Obviously cosine of t goes both positive and negative, but the negative parts, when you square cosine t to get cosine squared t, the negative parts come up above the axis, and so then cosine squared t looks like this, and the period is cut in half. It's no longer 2 pi, but in fact it's just pi. So, having observed that, and I'll make another remark here, which we will come back to later, but it says, interestingly, the fundamental period of cosine of nt is equal to pi if n is a positive even integer, like cosine squared t, but it's equal to 2 pi if n is a positive odd integer. And as I said, we'll return to this point later. So in this case, t naught is equal to pi, and omega naught is equal to 2 pi over t naught, so that's 2 pi over pi over 2. And since cosine squared of t is an even function, bn will be equal to 0 for all the terms, all those positive integers in other words, all the terms that you would have here in this summation, all the positive integer values of n. So let's now go ahead and calculate all the a's. Since the b's are all 0, let's calculate the a's. So we begin with a naught, and you know that the formula from your table is 1 over t naught, integral minus t naught over 2 to t naught over 2 f of t dt. And so since t naught is equal to pi, that becomes 1 over pi, integral minus pi over 2 to pi over 2 of cosine squared t dt. And if you look at Wolfram alpha or wherever you like to go to do these kinds of integrals, you'll get this 1 over pi term we bring over, and the value of this integral is pi over 2. And so 1 over pi times pi over 2, we get 1/2. So a naught is equal to 1/2. So now that we have that a naught is equal to 1/2, let's see what we can get for the an, where n is a positive integer. So the formula we have for this from table 5-3 is an equals 2 over t naught times integral minus t naught over 2 to t naught over 2 of f of t cosine of n omega naught t dt. And so in this case, since t naught is equal to pi and omega naught is equal to 2, that will become 2 over pi times the integral from minus pi over 2 to pi over 2. And then, of course, f of t in this case is cosine squared t. And as I said, omega naught is equal to 2, so this is cosine of 2 nt dt. Now, if you this is jumped somewhere else, and now I'm having trouble finding where I was. Let's see. Okay, so if you so this is where we were right here, and if you substitute this integral into Wolfram alpha, the expression that you will get is this. And this formula deserves some very careful consideration. So let's see what we have here. Now remember that we have already found a0. So we're finding the an's here, and this formula for an is used when n is equal to a positive integer. So that's why I have noted down here n equals 1, 2, ... But we're only using this formula for positive integer values of n. Now, the first thing that you notice is this sine pi n term in the numerator. Now, in a previous problem we did in lecture 21, we observed that sine of pi n is equal to 0 whenever n is a positive integer. So your first inclination might be to say that all of the a(n)s here are equal to 0, because after all of these are positive integers. In fact, sine of pi n is also equal to 0 for negative integers or for 0, but right now we're interested in positive integers, so let's just restrict our attention to that. But anyway, sine of pi n in the numerator is equal to 0 for every single n under consideration, and so you might be tempted to immediately conclude that all of these a(n)s are zeros, and so that part of the summation just drops out. But you can't be quite that hasty, because if you look carefully, you will see that the denominator of this will also go to 0 for one of the values of n in that range. Now, in this range, from for the positive integer values of n, there's only one value of n for which the denominator will go to 0, and that is n equals 1. For all other values of n, the denominator will not be equal to 0, and so in those cases, it's okay, in fact, to say that the numerator is 0, the denominator is not 0, and therefore a(n) is equal to 0. But for n equals 1, we have to be more careful. And that's basically what this is saying right here. Note that a(n) is equal to 0 as long as n is not equal to 1, but what is a1? Okay, well, to answer this question, what we're going to have to do, notice that this expression for n equals 1, it has the form of 0 over 0. And as you might remember from your calculus course, what we do in a case like that is to use L'Hopital's rule. And so let's do that in this case as well. So we have the 2 over pi right here, and instead of evaluating this at n equals 1, which would give us 0 over 0, what we'll do is we'll take the limit as n goes to 1, and we take the derivative in the top with respect to n. So we're having, I guess I go even more slowly step by step. So, so this is what we have at first. We're going to take the limit, rather than evaluating this exactly at n equals 1, we're going to take the limit as n goes to 1. And since that's going to give us a 0 over 0 when we don't know what that's equal to, then we use L'Hopital's rule. And so we take the derivative of the numerator with respect to n, and that gives us pi cosine of pi n. We also take the derivative of the denominator with respect to n, and that gives us 2 minus 6n squared. And now, if we take the limit of this as n goes to 1, we no longer get an expression of the form 0 over 0. Instead, what we would get, let's see, in the top, we get cosine of pi, which is negative 1 times this pi, so we get negative pi in the top, and in the bottom we get 2 minus 6, which is negative 4, so we're in good shape. And so what this is telling us then is that the limit of this expression, or the value of this expression as n goes to 1, is actually pi over 4. And then we need to multiply that by this 2 over pi out front, and so we get 1/2. So a0 is equal to 1/2, a1 is equal to 1/2, and all other values of a are equal to 0, and all of the bn's are equal to 0. So when we take all of that into account, we get cosine squared t is equal to a0 plus a1 cosine of 1 omega naught t, so that's cosine 2t. So we get 1/2 plus 1/2 of cosine 2t, which is exactly the same result that we obtained above using an entirely different approach. So, here, just to remind you, this is This is the same formula, but we arrived at it using an entirely different approach. So I really do think that this is quite interesting, that we can use the Fourier series in this way to get this very useful formula. And keep in mind as well that what the Fourier series is doing is it's telling us about the different frequency components of the function under consideration. So it's telling us that cosine squared t has a dc component, which is equal to 1/2, and then it also has this omega equals 2 component, which also has a magnitude of 1/2. And one more comment I would like to make is that, okay, this dc component, that the period of that can be considered to be anything. And I mean, we don't generally talk about the period of a constant signal, because anything you picked, it would work. But the period of of this term here that has omega equals 2 is pi. And so the overall period of the sum of these two components is going to be, in fact, pi, which agrees with what we said earlier about the period of cosine of t raised to an even power. So that's how we would do this problem, example 22.1, of finding the Fourier series of cosine squared of t. And so now we'll look at something a little more involved. First example. And now let's look at another example. And here, as you might have expected, what we will do is look at a higher order of power, a higher order of cosine, and this time we'll look at an odd one to see how it goes. So again, remember I said that the period in this case will be 2 pi rather than pi, because this function still goes negative for some values of t. Cosine squared t never goes negative. The cosine to the 5th t will have both negative and positive parts. So t naught is equal to 2 pi. And so omega naught is 2 pi over t naught, or 2 pi over 2 pi, which is 1. And cosine to the 5th t is an even function, so all of the bn's in the summation will go to 0. And now let's find out about the a's. Okay, well, the formula for a naught, as usual, is equal to this. And since t naught is equal to 2 pi, that becomes this. If you plug that into Wolfram alpha, you find out it's actually 0. Okay, what about an? Well, the formula for an is this, which when we plug in t naught equals 2 pi becomes this. And now when we use Wolfram alpha on that, we will get this expression. Now, this looks horrible at first because, just like before, we have this sine n pi in the top. So that makes it look like all of these coefficients are 0. But you remember that we can't say that for any value of n that makes the denominator go to 0. But how are we going to find the roots of a 6th order polynomial? Well, there is a hint. Let's think about what we had up here. Up here, when we used Wolfram alpha, we had the roots were n equals 0. Wait just a second here. Okay, we had n equals 0, and n equals 1. So if we try okay, let me resume with what I was trying to hint at was this. In our expansion up here, in our Fourier series for cosine squared t, which of course is an even power of cosine t, we had a DC component, which is like frequency 0, and then we had frequency 2. So the even power had these even frequencies, 0 and 2. So when we come down here to an odd power of cosine t, we're now cosine to the 5th t, that might make you think to look for odd powers. Now, omega naught is equal to 1, and the terms then in the expansion, Bn is equal to 0, so the terms in the expansion are going to be, you'll have A naught plus the summation n equals 1 to infinity of an cosine of nt, not 2nt like we had before, because in the previous case, omega naught was equal to 2, and so we had cosine of 2nt. But here, omega naught is equal to 1, so we just have cosine nt. And again, since we're looking at the Fourier series of cosine to the 5th, we would expect, maybe based on what we did before, that we will come up with the odd frequencies. In other words, cosine t, cosine 3t, cosine 5t, etc. So that leads us to believe down here that maybe 1, 3, and 5 would be roots. And if you guess that, you will find out that you would be correct. In fact, this polynomial in the bottom can be written as n squared minus 1 times n squared minus 9 times n squared minus 25. So the 6 roots are plus or minus 1, plus or minus 3, and plus or minus 5. Now, we don't need to worry about the negative roots because the index of the summation only has positive values. It starts at 1 and then goes 1, 2, 3, ... So we don't have to worry about the negative roots, the negative values of n. But the positive values 1, 3, and 5, we do have to concern ourselves about, because for those 3 values of n, this expression is going to have the form 0 over 0. And so once again, we will use L'Hopital's rule to evaluate the coefficients in those 3 cases. But in all other cases, we can say that the coefficient is equal to 0. Why? Because in any other case, if any other positive integer value of n, the denominator will not be 0, but the numerator will be 0 because of this sign in pi. So, so we only have 3 coefficients that we're going to have to worry about. And as I said, for each one, we will use L'Hopital's rule just as we did before. So the way this goes then, again, we're going to use this formula over and over. So for n equals 1, this becomes minus 1 over pi, and then 2n becomes 2 times 1. And then we have n to the 4th becomes 1 to the 4th, minus 30n squared becomes minus 30 times 1 squared, plus 149 we bring down. And then now for n equals 1, the term in the bottom that we have to worry about is n squared minus 1. So we're going to carry that over here. But the n squared minus 9 becomes 1 squared minus 9, n squared minus 25 becomes 1 squared minus 25, and then the 0 over 0 part is sine n pi over n squared minus 1, and we take the limit of that as n goes to 1. Okay, we can evaluate all of this stuff to get minus 1 over pi times 240 over 192, and then using L'Hopital's rule for this, we get pi cosine of n pi over 2n, and take the limit of that as n goes to 1. And so when we turn the crank on all of this, we will get simply 5/8. When we do the same thing for n equals 3, okay, this time we will need to take the n squared minus 9 under the sine n pi, because when n is equal to 3, that's the term that will go to 0 in the denominator, and then we leave n squared minus 1 over here. And so, but that's the only difference from what we had before, except that now we evaluate for n equals 3 rather than n equals 1. And when we do it, and again use L'Hopital's rule for this, and as I said, evaluate at n equals 3 instead of n equals 1, we will get 5/16. And then finally, doing it one last time for n equals 5, okay, when n is equal to 5, the term n squared minus 5 is the one that goes to 0 in the bottom. So that's the one that will be taken over here to evaluate with this in this fraction like this. And then the limit will be taken as n goes to 5, and all the rest of the expression will stay over here. And when we do that, this time we will get this, and take the limit as n goes to 5, and when we turn the crank on all of that, we get 1/16. And so putting together that information, remember A0 was equal to 0, all the B's were equal to 0, and all the AN's were equal to 0 except for these three. So we get 5/8 cosine t plus 5/16 cosine 3t plus 1/16 cosine of 5t, and that's it. That's the entire Fourier series for cosine to the 5th of t. And notice, getting back to what we talked about earlier, the cosine t, that's omega is equal to 1, so the period of this part is 2 pi. Cosine 3t is omega equals 3, so t is equal to 2 pi over 3. And for this last part, omega is 5, t is equal to 2 pi over 5. So this t right here for the first term is 3 times that one and is 5 times that one. So this t would also be a period for these two functions. It's just not the fundamental period. And so this is like problems we had on the first test, where we had this, the sum of multiple sinusoids of different frequencies, and what we tried to do was to find a period that worked for all of them. And so t equals 2 pi is the smallest period, the smallest number that is a period for all three of these functions. And so t equals 2 pi is the overall period in this case, where we have an odd multiple of the an odd power of the cosine of t. So what we can say is, when you have an odd power of cosine, the first term is going to be cosine of t, and so it will have a period of 2 pi, and the others will be like this: 2 pi over 3, 2 pi over 5, 2 pi over 7, 2 pi over 9, and so the overall period will be 2 pi when you have an odd power of cosine. But when you have an even power of cosine, like cosine squared t, then you're going to have a situation like this. You'll have a constant term plus cosine 2t plus cosine 4t plus cosine 6t, and so on. And so now the DC component, as I said, you can consider the period of that to be anything, but this cosine 2t is the first thing that has a definite period, and since omega is equal to 2, t is equal to pi. And pi is also a period of all the subsequent terms, but it's not the fundamental period. T equals pi is the fundamental period of this. So overall, it's the fundamental period of the whole expression. And therefore, that helps us to see why the fundamental period of cosine of an even power of t is pi, while the fundamental period of an odd power of cosine t is 2 pi. And that insight comes from looking at the Fourier series. So, and as I said, we made the connection here with an identity you learned long ago when you were doing integrals in calculus. And so I just think this is really an interesting application because, you might have run into an identity like this before and never thought of that as being a Fourier series, but that's exactly what it is. And so that's just a really nice demonstration of how, as I said before, the Fourier series helps you to see the different frequency components in your signal. And that is really valuable. And we will, in our, either in the next lecture or the one after that, in the very near future, we're going to find that Fourier series also has a really interesting application to phasor analysis. So anyway, that concludes lecture 22, and I think you should be in good shape now for test 22. So good luck.